Hey, Unites, hope you had a good weekend. Welcome to Monday's session. Today we're going to take a look at putting trigonometry together. So these are your application problems, which is your worded problems. But before we do, we have to understand what the angle of elevation is and what the angle of depression is. So imagine we have a cliff. So let's say this is a cliff. If you couldn't recognize from my artistic artwork. If you were lying at the top of this cliff and yep, that's brilliant. And you were looking into the water. Actually, let's make water blue. If we were looking into the water and you spot a little boat. That's pretty nice. What we call the angle of depression is if we were to dot the land like so to continue the flat surface of the cliff onwards into the water. If I were to look down at the boat, okay, this angle here is what we would call the angle of depression. Angle of depression. Imagine when you're depressed, you're looking down, or I don't know, you depress your heads downwards. I don't know if that makes any more sense than the previous statement, but the angle of depression is commonly mistaken. A lot of students usually put it here on the test, which is incorrect. It's actually if you extend the cliff landmass that you're lying on into the water, then the depression is between the sight line of you seeing the boat and the landmass continued into the water. So that's that spot there. The angle of elevation, on the other hand, is this angle in here. All right, what you'll notice is they're both represented by theta, implying the angle of depression and the angle of elevation will also be the same. So this here is the angle of elevation. In other words, if I was a person sitting on this boat and I was, for some reason, sailing my boat right into the face of the cliff, and if I looked up at the person lying on the edge of the cliff looking down at me, when I tilt my head upwards and see the person lying down on the top of the cliff, that's the angle of elevation. I hope this sort of makes sense. This angle here is always going to be the same as the angle of depression. That's going to be an important point. All right, so let's write down here the angle of, we'll stay with that. Elevation is always, no matter what, always the same as the angle of depression. Now, why is that the case? Because these two are complementary angles to each other. All right. Again, if you're interested for the proof, let me know. Send through an email, but we'll leave it at that. As long as you know that if you find the angle of depression, you found the angle of elevation also. Hopefully this makes more sense with some examples, so let's do one together. Or, matter of fact, let's do three together, because this is some pretty tough stuff for some of you who might not be able to read so well. Right, so the angle of elevation, straight away we've got to underline the key details. In example 1 here, they're telling us the angle of elevation to start with from the top of a tower from a point on the ground 30 meters away from the base of the tower is 28 degrees. Find the height of the tower to the nearest meter. Right, so the angle of elevation of the top of a tower from a point on the ground 30 meters away. Let's just draw this first. So top of the tower. Top of tower. Let's draw our tower. Imagine it's like the Washington Monument. Pretty good, huh? So this, I'll just label it in case you guys aren't sure what this is. This is our tower. That's the top. Okay, from a point on the ground, 30 meters away from the base. So let's say this is the point on the ground. Again, I'll label it point on ground. And we know point on ground is 30 meters away from the base. In other words, this distance to that distance there is 30 meters. The angle of elevation, remember, here is 28 degrees. So what that means is if we were lying down at this point on the ground, to see the top of the tower, we would have to tilt our heads 28 degrees to see the top of the tower. All right, find the height of the tower to the nearest meter. So what we're trying to find is the height. And if we highlight that, height of tower, we have in H. I hope the information we've gotten so far is making sense. So that point there is the top of the tower. What we need to do is see if we can see the triangle. From my brilliant artistic drawings, can you see the right angle triangle that we're dealing with to find the tower? Yes. Well, hopefully yes. The right angle would be here. Okay, we've got pretty much a triangle that looks like this. So if we abbreviate this triangle, that's awful. If we abbreviate the triangle, what we have is a right angle triangle. There's our 28 degrees. All right, here's our height. Down here, we've got our 30 meters. And what we can do is apply what we've learned from the previous exercises to find H. So what's the first step? I might just highlight just in case if people are like, well, what are we looking at? So that's the top of the tower. And that's interior angle. All right, so this drawing here has just turned into a stock standard 2D triangle. So step one, what's step one? Step one is to label the given sides, if you recall. All right, so what we're given here is the adjacent, all right, because it's touching the 28 degrees and it's not the long side. So in other words, it's not the hypotenuse. What's a height here, or this height side? Again, this isn't the H for hypotenuse. This is actually the opposite. All right, so this is the O. So out of sine, cosine, and tangent, which one do we pick? Remember the acronyms are SO, CA, TOA. Are we given the opposite and hypotenuse? No. Are we given the adjacent and hypotenuse? No, we don't have hypotenuse given to us here, or we don't care about it. Are we given the opposite and the adjacent sides? Yes, we are. So we are going to pick tangent here. All right, so what we do here is we write out our generic formula, tan theta equals the opposite over the adjacent. And from there, we proceed to plug in our values, if you recall. So our values from the triangle, we have 28, which replaces the angle. The opposite side here is h for height of the tower, and the adjacent side is 30 because that's the distance from the tower to the point on the ground. Once we've done that, what we need to do is we notice the 30 is at the bottom of the fraction. So when 30 is at the bottom, or when the pronumeral is at top, we chuck the 30 to the other side and multiply it with the tan 28 degrees. Times 30, which would equal the height. So once we've got tangent 28 times 30, put that into your calculator. All right, so tan 28 times 30 gets us 15.95. But make sure you don't forget the units. What we're dealing here with is meters. And the question says, find the height of the tower to the nearest meter. All right, so we got to say this is 15.95 meters, which is equal to 16 meters rounded. And that there is our height. Cool. Hopefully that makes sense. If it doesn't, please let me know, either in the comments or by email. Example 2. From the top of a vertical cliff, so top of vertical cliff. Andrea spots a boat out at sea. Classic example, similar to the one that I drew at the very start. Okay, so Andrea here is lying down. Disturbing a little bit, but that's Andrea. Okay, spots a boat out at sea. Got our little boat. Okay, the top of the cliff is 42 meters above the sea level. So 42 meters is this section. The boat is 90 meters away. Let's use green. From the base of the cliff. All right, so from there to there, that distance is 90 meters. Find Andrea's angle of depression to the boat to the nearest degree. All right, so we're looking for the angle of depression. When we're looking for the angle of depression, we got to imagine this cliff face extends out. All right, Andrea's looking down at the boat like so. It's this angle here that we're finding, but remember the angle of elevation and the angle of depression is the same thing. So if that's our right angle, if we find the angle of elevation here, we'll find the angle of depression. So in other words, find the angle of elevation instead. Okay, to find the angle of depression. That's why that first statement is so important. So remember back on the first page, we wrote here, the angle of elevation is always the same as the angle of depression. So if we were to try and find this angle here, this is actually outside the triangle, similar to our example. So it's no use to us. We can't use trig to find an angle that's outside of the right angle triangle. So if we find the angle of elevation, then we can say, well, the angle of depression is the same as the angle of elevation. So we have our answer indirectly by finding the angle of elevation. So really we're finding this theta here. So let's try and redraw this triangle in a simplified 2D version. So what we have is our right angle here. That's our 42 meters. All right, that's highlighted in yellow. We care about this outside angle of depression, which isn't actually in the triangle. So instead, we're finding this theta in the bottom right corner instead. And our I guess our other side is 90 meters. It's not drawn to scale. I probably should have drawn it to scale, but you get the gist. Nothing in maths is to scale. Right, so now that we've drawn our 2D triangle from our complicated scenario, hopefully you can see how this triangle here translates to this triangle here. So once again, to find this angle on the inside, which is our angle of elevation, we have to label the given sides. So what's the 42 side? This is our side that's small and furthest away from the interior angle, which is called the opposite. This 90 side is not the long side, but one of the shorter sides, and it's touching the interior angle, which means it must be the adjacent. All right, because the adjacent means next to the angle. And so if we were to write Katoa down to pick either sine, cos, or tangent, which one would we use? Are we given the opposite and hypotenuse? No, we're given the opposite and adjacent. So that means anything with a hypotenuse in it, we're not choosing. Once again, it's going to be tan, the one that we choose, because tan has the opposite and the adjacent sides when we compare them. So we write our generic formula of tan theta equals the opposite divided by the adjacent. And what we're left with is a situation where we've got to sub in our values from the triangle on the left, which means tan theta is still a mystery because we're trying to find that interior angle, which is our angle of elevation. And our opposite side is 42 meters. So we sub in 42 instead of having opposite. And our adjacent is 90 meters. Right, once we've got this down, to get tan to the other side and get theta by itself, we inverse it on our calculator and we sub in, well, not sub in, we just type in 42 divided by 90, or 42 on 90, depending on what sort of function your calculator can do. And then you would have to shut the brackets and press enter to get your correct answer. So let's see what we get. Tan inverse, 42 on 90, shut the brackets, gets us 25.02. We're talking about angles here, which is degrees, which is equivalent to 25 degrees because the question up the top, if you recall, says to the nearest degree. So our angle of depression is therefore 25 degrees, okay? So this angle here is 25 degrees and this angle here is 25 degrees. In other words, both our angle of depression and angle of elevation, depression from the person at the top of the cliff and elevation from the person at the boat, is both 25 degrees. I hope that makes sense so far. Let's take a look at one last example. This one's the super trickiest out of them all. In fact, this one they give us a diagram to accompany the question. So we don't need to deal with my sort of artwork because I suck at drawing aeroplanes. Let's take a read. Well, let's have a read. A plane flying at an altitude of 1,500 meters. Okay, as we can see here, 1,500. It starts to climb at an angle of 15 degrees. So in other words, this plane is going to climb, or having to clear the mountain. It's going to try and navigate it by increasing it by 15 degrees to the horizontal. Okay, the horizontal is obviously parallel to the ground, and hopefully now you can sort of see our right angle triangle developing. 15 degrees. Okay, so angle of elevation, 15 degrees. When the pilot sees a mountain peak 2,120 meters high, the plane is 2,400 meters away from the mountain. Are we going to clear it? Okay, so I've highlighted all the details that's corresponding to the diagram. Will the pilot clear the mountain? Well, firstly, what the question is saying is a yes or no. All right, so yes, he clears, or no, he doesn't. So what we need to understand here is we need to redraw this right angle triangle from the information that we're given. Oh, that's nice. It's probably the best right angle triangle I've done online since forever. The interior angle here is 15 degrees. There's sort of two ways to go about this. You can either find the angle you need to clear the mountain, or you simply go and see what happens if he flies at 15 degrees and we find this missing side. All right, so the X would go here. All right, so that's sort of my opinion. We go and find the X. All right, so let's find this X that we've we're out of colors. Let's go find this X, which is in orange. Okay, this 15 degrees is from what we highlighted in green. From above, we know that the plane is 2,400 meters away, which is the part in purple. All right, so if this aeroplane is going to fly at 15 degrees for 2,400 meters, how high out does the plane get from where they were back 2,400 meters away when they get to the mountain? Let's see what we get. So again, what we need to do is we choose either SOHCAHTOA or TOA, or sine, cosine, and tangent. Are we given, well, let's label the sides. Are we given the hypotenuse? No. So what's this purple side? This purple side here is one of the shorter sides, and it's touching the interior angle. So it's next to the interior angle, which means it's the adjacent. All right, the right angle, remember, is always opposite the longest side, or the longest side is always opposite the right angle. So we know that side there is a hypotenuse and not the purple. The orange we have in X is our opposite. So once again, which one has opposite and adjacent? Is it the sine ratio of opposite and hypotenuse? No. Is it the cosine ratio of adjacent and hypotenuse? No. Is it the tangent with adjacent and opposite? Yes. I got the O and A the wrong way around. So what we do here is we go and say tan. I hope I didn't get that the wrong way around, the other ones. Oh. Yeah, how bizarre. So what we say here is tan theta, which is our generic ratio, equals the opposite value divided by the adjacent value. And what we notice here is the interior value we know is 15 degrees, which is the angle of elevation the plane's climbing at. The opposite side length is x, and the adjacent side length is 2,400. Now, we've got x on top. So to get x by itself, right, we chuck the 2,400 to the other side. $2,400 equals x. Right, so now that it's put to the other side, we can input tan 15 times 2,400. Tan 15 times 2,400, which would get us 643 meters and 8 centimeters, right? 4.8 meters, which is 8 centimeters. That's going to be our x. Let's take a look back at our diagram though. How far off is the pilot from the peak of the mountain? So the pilot, or in other words, a plane, let's use plane. The plane needs 2,120 meters, which is the mountaintop, the top of the mountaintop. Take away 1,500. To clear the mountain. To clear the mountain. Okay, so this part here, well, basically the pilot needs to fly at least, what's 2,120, take away 1,500, 620 meters. Okay, so the pilot needs to clear at least 620 meters to pass through the mountain unharmed. We fly 643 meters by the point we hit the mountain, so yes, we have cleared the mountain. All right, so therefore, if we fly at 15 degrees elevation from 2,400 meters away, we will clear the mountain by 23 meters and 8 centimeters. Okay, so how do we get this 23.08? That's 643.08 take away 620. Okay, so this is 643.08 take 620. All right, so long story short, will the pilot clear the mountain? Yes, by 23 meters and 8 centimeters. All right, so that's it for exercise 3I. Please have a go at the questions, which I will post in the Google Classroom. All right, thanks everyone.